Welcome. In this video, I'm going to get started with multi-level feedback queue for spring 2022. So let's just review the different algorithms. There are 3 queues. So all of the processes will start out at level 1 queue. So level 1 queue is round robin with a time quantum of 8 time units. Q2 is round robin with a time quantum of 12 time units. And Q3 is just first come, first serve. So all processes are initialized at time 0. That means that the arrival time for each process is time 0. So they all arrive and are ready at time 0. And we're assuming that they arrive in this order, P1, P2, P3, etc. So we're going to assume that they all arrive in the process number order. So let's get started. So when if a process is CPU burst is longer than the time quantum, then it gets moved down to Q2. If a process gets moved down to Q2, then it is a level 2, and level 1 has absolute priority over all other processes with preemptive priority. So if a process gets moved down to Q2 and it happens to be a Q2 process on the CPU, it will possibly be preempted by a level 1. All right, so let's get started. At time 0, we have P1. P1 has a CPU burst of 7 time units, which is smaller than the time quantum of 8. So P1 is going to be on the CPU until time 7. It's going to go out to I/O for 22 time units, and it will arrive back at time 29, and it will remain a Q1 process. P2 is going to get 8 time units on the CPU until time 15, at which time it will be preempted, and it will go off to, it'll go back. It doesn't go off to I/O, it goes back into the ready queue, and it will have 6 CPU burst time units left, and it will arrive back in the ready queue at time 15, and it will be now a Q2 process. Now the current time is 15. The next one to go will be P3. P3 gets 8 time units on the CPU. It has a CPU burst of 8 time units. We'll go out to I/O for 43 time units. So it will come back into the ready queue at time 66. Then now the current time is 23. We have P4. P4 is going to get 8 time units on the CPU. It'll be preempted at time 31. So it'll go back into the ready queue, directly back to the ready queue, become a Q2 process, and now it will have 5 time units of CPU burst left. The current time is 31. The next on the CPU is P5. P5 is going to have a CPU burst of 6 time units. It's going to go out to I/O and come back at time 71. And remain a Q1. Next on the CPU is going to be P6. P6 is going to go until time gets 8 time units until time 45, and it's going to go down to a level 2, come back in at time 45, and have 1 CPU burst of time left. Current time 45, the next one to go is P7. P7 gets 8 time units. It's going to be preempted at time 53. Go back into the ready queue at time 53. And we'll have 6 time units left. The current time is 53. The next one to go is P8. P8 gets 4 time units until time 57, goes out to I/O, and will come back at time 121. Hopefully my math is right. All right, and now the current time is what was that? 64. 6 and 5 is 11, 12. Yes, that's correct. Okay, now the current time is 57. Now P9. P9 is going to get 8 time units until time 65. It will be preempted at time 65. Will become a level 2. We'll have 5 time units left of its CPU burst, and we'll get back into the ready queue at time 65. All right, so now we've gone through all of the processes, and at this point you can actually calculate the response time. P1 response time is 0, P2's is 7, P3's is 15, etc. So you can now calculate the response time. The response time is the first measure of waiting time. Remember that the turnaround time equals the CPU time plus the I/O time plus wait time. And wait time is all of the time that the process spends sitting ready for the CPU. So the processes when they're out in I/O, they're out in I/O. And I/O just means that they're out there doing something else. They're not ready for the CPU. So they're not in the ready state. They are in the blocked state or an event state. So they go out to an event and they are not in the ready state. The ready state is when they are actually waiting for the CPU. So if you take a look at this at time 65, we have P1 has been waiting for the CPU, P2 is in the ready queue, P3 is still out in I/O for one more time unit, P4 is in the ready queue, etc. So, this is not the way that you implement, because when you implement, you don't really use the arrival time. You deduct from the I/O time until it gets to 0, and then when it gets to 0, it gets back in the ready state. But as a person looking at this is the way that I do it. I keep track of the arrival times. All right, so the next thing we want to look at is the fact that we have some Q2 processes. Those are lower priority, and when they get the chance, they do round robin with time quantum 12. But they don't get the chance as long as there are any Q1 processes in the ready queue. So we're going to take a look now, and we will notice that there is one Q1 process in the ready queue right now, and that is P1. So P1 is going to get the ready queue again, and if P1 CPU burst was greater than 8, then it would be dropped to Q2. Once a process drops down to Q2, it does not go back up. So P1 has a CPU burst of 6 time units, so it will be on the CPU until time 71, at which time it will then go out to I/O for 19 time units and will come back at time 90, and it will remain a level 1. All right, now the current time is 71. In our ready queue, we have P3, P2, P3, P4, P5, P6, P7. So all of these are in the ready queue, and P9, right? But some of them are Q2. So right now we only care about the Q1s. So in the ready queue, what Q1s do we have? We have P3 and P5. P3 got there at time 66. P5 just got there, so P3 goes first. P3 will go until time 78. And then go out to I/O for 41 time units and come back at time 119. Hopefully I'm doing my math right. If I was doing this, not recording, I would make sure I have a calculator to check my math. All right, now the current time is 78. We have the only Q1s in the ready queue. We do not, P8 is still out at I/O. P5 is in the ready queue, P3 is still at I/O, P1 is still at I/O, so now we get P5 will go next. P5 will go for 7 time units until time 85, and then P5 will go out to I/O for 21 time units and come back at time 106. Current time is 85. We do not have any Q1s in the ready queue at this time. If you take a look at all of our Q1 processes, they are all still out in IO. So the next one to go, we're going to check our Q2s. So we have in the ready queue of Q2s, we have P2, P4, P6, P7, and P9, but the one that got there first would be Q2. So the thing about it is when you have level 2 processes on the ready queue, and this is a hard part about this algorithm, because you're not just doing round robin, you're also are checking for preemptive priority. So you have to check each time unit whether or not when a Q2 is on, you have to check for the arrival of Q1s. And if the Q3 is on, you have to check for the arrival of Q2s and Q1s. So P2 is going to get started, and P2 has a CPU burst of 6 time units. So 6 time units is definitely less than the time quantum of 12, so it should be able to do all 6 time units. But if you look here at time 90, so at time 90, we're going to have P1 arrive. P1 is going to arrive back into the ready queue at time 90, and P1 has a higher priority than Q2, so we're going to be using preemptive priority to kick P2 off at time 90. So P2 is going to get kicked off at time 90. It's going to go back directly to the ready queue at time 90, and now it's still going to have one more time unit of CPU burst left. And now P1 is going to get its chance, is going to get it onto the CPU. And look at this, P1 has a CPU burst of 12, so P1 is going to get to go onto the CPU for 8 time units until time 98, at which time it's going to be kicked off. It's going to go back to the ready queue at time 98. It's going to have 4 time units left of its CPU burst, and it will be changed to a Q2 level process. So I hope that this answers some of your questions. I just want for your assignment, just for you to run through this algorithm up till time 200 and whatever I said, so that you get a feel of this algorithm and what's happening, so you can practice, so you can start your implementation. This is a really, really good assignment for students to challenge themselves and see if they can complete the implementation of this algorithm. It's much more challenging than the shortest job first. So I want to make sure, but it's very important that you understand the algorithm. There are 2 things going on here. There are processes that have different queues. In each queue, they have a different algorithm. Once they get down to a lower queue, they stay in that lower queue. But then you also have, based on the queue level, there is preemptive priority. So preemptive priority makes it complicated, and but it's very important that you understand the algorithm so that you can write your code implementation. So I hope that this helps.